This video shows you how to estimate a multivariate linear model with the method of maximum likelihood. The linear model of concern is a VAR1 model. I introduced the estimation concept with an example. Now here's the setup for the example. Assume xt is two-dimensional, meaning xt is a column vector consisting of ut and vt. Both are observed. And assume that time goes from 1 to capital T. So the VAR1 has a constant mu and an autoregressive matrix A and a volatility matrix C. So the entire VAR1 can be written as follows. In order to be very student-friendly, I wrote down explicitly the last equation in terms of ut and vt. So note that the product of volatility matrix times structural shock can be written as a statistical shock, meaning C times eta t is equivalent to epsilon t, where epsilon t is an IID variable with mean 0 and covariance matrix sigma. And it holds that sigma is equivalent to C transpose. So in summary, we now want to apply maximum likelihood to estimate the multivariate linear model of type xt equals mu plus axt minus 1 plus epsilon t, where epsilon t is an IID shock with mean 0 and variance sigma. Now the first thing we have to do is we need to take a stand on the distribution of epsilon t. Now let's work with the simplest case, namely a multivariate Gaussian distribution. In that case, we have that the implied probability of having observed xt conditional on the observation of xt minus 1 and conditional on the VAR1 parameterization is given by the following term. And note that the epsilon t is simply the xt minus the mu minus axt minus 1. And the dimension of xt in our example here is 2. So we can now express the likelihood of the parameters mu, a and sigma conditional on the observed panel xt and conditional on epsilon being indeed multivariate Gaussian. So the respective likelihood for mu, a, sigma conditional on xt is the product from t going to 2 to capital T of the probability of xt conditional on xt minus 1. Now note, I leave out the unconditional probability of x0. In order to be very clean, we would have to multiply in that unconditional probability. Now I leave that step aside for that video here to focus on the essentials. More importantly, for sufficiently large capital T, the solution to the parameter estimates is unaffected. So we can now plug in the parametric expression for the last term for that conditional probability and take everything that doesn't depend on time in front of the product operator. Now that gives us that the likelihood of our parameters conditional on the xt panel is given by the following expression here. Now, the log likelihood of the parameters is then given by the following expression here. So what we now do is we are now going to look for the parameters mu, a and sigma that are maximizing that log likelihood function. Now, let me end the video with some practical remarks. First, it is not a good idea to just hand over the optimization problem to a computer and to stop the thinking. Numerical optimizations are a delicate task, especially if you want the correct solution for a system that isn't small anymore. And if the model has nonlinearities, then the task is even more complicated and more fragile. Therefore, second, I advise you help the numerical routine by exploiting as much of the parametric structure as you can. For example, if the covariance matrix sigma was equal to the scalar sigma times the identity matrix, and if you have a linear model, then the solution for mu and A can be separated from finding the scalar sigma. You can see that when analytically computing the gradient of the log likelihood function. In that case, the MLE solution for mu and A does coincide with the OLS solution. The MLE for sigma is then simply 1 divided by t minus 1 times the sum from I equals 1 to t minus 1 of epsilon I transpose. Now, my experience in the classroom is that students underestimate that importance of that recommendation. And only if they actually solve larger problems, they are realizing how important it is to exploit structure before handing it over to a computer. Third, even if the covariance matrix is multivariate, you can learn from OLS versus GLS the following. For GLS, you iteratively run a OLS first, and then you take the OLS residuals as a starting value for the covariance matrix of errors. And I recommend you try using that same logic for running MLE estimations. And the more you can help the numerical search routine, the larger the problems that you will be able to master.
Got feedback? We would love to hear it. Please drop us a line. And if you liked the video, give it a thumbs up. And don't forget to subscribe to the channel.